You may recall from general chemistry that kinetics is the study of the concentration of reactants versus the rate of the reaction. So as an example, an alkyl halide that is secondary, when mixed with the hydroxide ion will displace the bromine with inversion of stereochemistry, as you see here in the product. If we do different experiments where we're varying the concentration of each reactant, we can observe how the rate of that reaction is affected. So as an example, experiment 1 has a concentration for each reactant of 0.1 molar, both for the alkyl halide and for the sodium hydroxide. If we double the concentration of the alkyl halide in a separate experiment for this particular reaction, we notice that the rate of the reaction doubles as well. In a third experiment, if we keep the concentration of the alkyl halide the same as the original experiment, but this time we double the concentration of the sodium hydroxide, we would observe a doubling of the rate of the reaction as well, similar to the second experiment. So for this reaction, based on these kinetic studies, we can determine that the rate equation is equal to a constant K times the concentration of the alkyl halide raised to the 1 power times the concentration of the sodium hydroxide raised to the 1 power. So overall, this rate equation is second order overall. So we get that by adding the two exponents. 1 plus 1 would make this a second order overall reaction. Based on these kinetic studies and also what we observed in the last slide, where there is an inversion of stereochemistry when we do a substitution of secondary alkyl halides, we now have two pieces of evidence for the SN2 reaction. All right, so based on what we learned from the kinetic studies and also the fact that we believe that the SN2 reaction gives a product with inverted stereochemistry, we could come up with a reasonable mechanism for the SN2 reaction. So we believe that the nucleophile, in this case the hydroxide ion, attacks the carbon that contains the bond to the leaving group from the backside. So that would clearly explain the inversion of stereochemistry. Now, why does that happen? Well, one reason would be if we look at the transition state, the incoming nucleophile, the hydroxide, has a partial negative charge, and also the leaving group has a partial negative charge. So it would make sense that these two parts of the molecule would want to stay away from each other to avoid repelling the two negative charges. From there, the final product is formed where the OH is attached on the opposite side of the molecule that the bromine used to be attached to. And so therefore we get an inversion of stereochemistry. Now that we have learned some of the basics of substitution reactions, and we cover a little bit of SN2, it's a good time to maybe review some of the terms that we learned. So in this question, we want to identify the nucleophile, electrophile, and leaving group. So I'll give you a moment to think about it, and then we'll cover the answer for this. So here is a typical SN2 reaction involving a primary alkyl halide with sodium iodide. The reaction leads to the iodine replacing the bromine, and you can see that in the product, and then we receive a byproduct of sodium bromide. The iodine is our nucleophile in this reaction, and we can figure that out by the fact that sodium has a +1 charge. So anytime you have a metal next to a halogen, that metal will typically have a positive charge. and then the halogen, in this case the iodine, would have a negative charge. So iodine in this example would have a -1 charge because it's next to the sodium, which has a +1 charge. The alkyl halide is our electrophile in this reaction, and particularly this carbon here is electrophilic site, since it's bonded directly to the halogen, which is our leaving group. So in this question, we want to predict the product from a reaction between 1-bromo-1-phenylethane with a cyanide ion. The question asks us to use the R stereochemistry for this carbon here, which is not shown. So we want to figure that out before we start. And we're going to react that with sodium cyanide. The cyanide ion, in particular this carbon here, is our nucleophile. And that would be reacting with this carbon of the alkyl halide. In this reaction, the cyanide ion would attack the carbon attached directly to the leaving group, the halogen. If we start with our stereochemistry around this carbon, the bromine would have to be drawn back, which means when the incoming nucleophile comes, it will come from the opposite side. As a result, the cyanide ion would be drawn facing towards us. Which would give us, in this case, the S stereochemistry.